Hi everyone. Assalamualaikum warahmatullahi wabarakatuh and a very good day. Today we are going to proceed discuss the tutorial 11 where it is on the formations of solid. So I'm going to focus on part B first today. Okay, we do question number 1 first. Okay, based on the question, given here we have a copper wire of length 3 meter and the radius is given, which is 2.4 millimeter. Then this copper wire is stretched by 1.5 millimeter when the load is suspended vertically at its end. And if the Young modulus of the copper wire is 1.2 times 10 to the power 11 Newton per meter square, so determine the mass of the rod. Okay, so determine the mass of the that one is not determine the mass of the rod, but determine the mass of the load. Okay, so from the equation here, from the question, it given the L naught of the copper wire is 3.0 meter. Right, the diameter of the copper wire is also given, which is 2.4 millimeter. Okay, and then instead of these two, the elongation is also given, which is 1.5 millimeter. And then the Young modulus of the copper wire is 1.2 times 10 to the power 11 Newton per meter square. So how to determine the mass of the load? If I sketch a case, okay, let's say I have the copper wire. So let's say that one is the copper wire that we tie vertically, and then at its end we have the load. Okay, so this one will be the weight of the load, which is equal to mg. So the force that stretch the copper wire for 1.5 millimeter is because of the load that we attach at the end of the copper wire and we hang it vertically. So to find the mass of the load, we need to use an equation of Young modulus. We have Young modulus equal to FL naught per AE, where in this case the force experienced by the copper wire is due to weight of the load. Weight L naught per AE. So the weight is equal to mg L naught per A elongation. So this one is the Young modulus. Okay, based on the information we know the Young modulus, the values of Young modulus, we can substitute it. Okay, the gravitational acceleration is a constant, okay, which is 9.81. The L naught is also given, which is 3 meter. You can substitute the 3 meter. And then the elongation is also given, which is 1.5 millimeter. But you need to change the unit to meter first. And then the A, even the A is not given, but we can find the A from the diameter given, because the A is equal to pi t squared per 4. But you can substitute the value of diameter in the formula in order to find the A. And then if all the value is known, then you just substitute in the formula to find the mass. So simply you can find the mass. Okay? Yeah, we assist you, and then you will do that one later. You do this one. Okay, for part B, question number 1, sketch the stress strain graph to show the extension strain change with the force on a wire, and then marks on the graph the following region. Okay, the first is region in which satisfied the Hooke's law, regions of elastic deformation, and the last we're supposed to mark the regions of plastic deformation. Okay, first we need to sketch the graph. Let's say here is my y-axis, this one is my x-axis. So we're going to plot the graph of stress, again strain. So for wires, okay, for tie wires, the shape of the graph that we're supposed to draw is straight. So straight initially, okay, and then curve a bit, maximum stress, and then the failure. Okay, then marks on the graph a few points. We have point A here, which is proportionality limit. Point B is the elastic limit. Point C is yield point. Point D is point of maximum stress. And then point E will be the failure point. Okay, then the region which satisfies the Hooke's law is, right, this one. Okay, this one is actually the region that satisfies the Hooke's law, because it is a straight line, shows that when the force or when the stress increase, the strain also will increase. Okay, this one is a line that satisfying the Hooke's law. Okay, we know here is Hooke's law. Okay, and then on the same graph, you also need to mark regions of elastic deformation. Regions of elastic deformation is, okay, just draw, a dotted line, pass through point B, because point B is the elastic point of elastic limit. So just mark here, this one is a regions of elastic deformation. And then from point C to the point E, point C to point E, right? This one is actually a regions of plastic deformation. Given a steel wire with 4.5 meter long, okay, being stretched for 0.15 centimeter, okay, when a force of 370 Newton load is applied. Given the Young modulus for the steel wire is 20 times 10 to the power of 10 Newton per meter. So what is the diameter of the wire? And then also, if we did desire to stretch be less than 0.15 centimeter, should its diameter be increased or decreased? Then you need to explain your answer. We just look at for question number 2, part A. Okay, given here, we're going to find the diameters of the wire. So how we find the diameters of the wire? Simply you are using an equation from a Young modulus, where we have Young modulus is equal to F L naught per A E. But then the purpose of doing this is actually to determine the cross-sectional area. Because from the cross-sectional area, we can find the diameter. Because for the area, cross-sectional area is equal to pi d squared per 4. So the diameter is in a cross-sectional area formula. So we do that one, we find the cross-sectional area first. So how we find the cross-sectional area? You need to rearrange the formula. So we have cross-sectional area is equal to F L naught per Young modulus E. Okay. So substitute the value because the force applied given 370. Okay. The L naught of a steel wire is given as well, 4.5 meter. The Young modulus for the steel wire is 20 times 10 to the power of 10. Okay, then the elongation is 0.15. So you got the answer in meter square for the area. Okay, so that right after find the cross-sectional area, substitute the values of this cross-sectional area in a formula of cross-sectional area for a circle. Because the wires is actually in a shape of okay, that is, yeah, this one is actually the wire cylindrical. It's actually shapes of cylindrical, the wire. So the cross-sectional area is here. This one you are using pi r square or pi d square per 4. Okay, so simply you can find the diameter from this, okay, from this equation. So the diameter is given is 0.27. Sorry, 0.27 here centimeter given meter times 10 to the power of -2 meter. Okay, this one is for part A. And then for part B, if it desire to stretch less than, okay, the stretch now is less than, the amount of elongation is less than 0.15 centimeter. So, should the diameter be increased or decreased? Okay, logically, if we go to stretch the wires less than the stretch amount, of course, the diameter is increased. Okay, put the answer first, diameter increase. Okay, why the diameter increase? From the equation cross-sectional area just now. Okay, where is the equation? Right, the equation is here, cross-sectional area. So I'm using the equation of this cross-sectional area equal to what? Is equal to F L naught per Y E, where A is pi d squared. A is pi d squared per 4. You see these two, elongation and diameter square. So the diameter square is inversely proportional to the elongation. If the elongation is less than the amount of elongation given, means that our diameter is bigger. So why the diameter bigger? Because why the diameter bigger? Because elongation and diameter is inversely proportional. Okay, for number 3, it seems quite simple with the two questions that we have discussed. Okay, because the question is just a straightforward question and then we're just using the formula. So for question number 3, given a meter wire, we have a meter wire with a uniform cross-sectional area. Okay, this one is cross-sectional area is given. The length is also given 20 centimeter, is acted by a force of 50 Newton. Okay, and the force of 15 Newton is acted at both ends. So determine the stress of the wire. So from the question, the cross-sectional area is given, but the cross-sectional area is 0.5 millimeter. Okay, and then the length of the metal wire is also given, which is 20.0 centimeter. And then the force applied is 50 Newton. So we're going to determine the stress of the wire. So how we determine the stress of the wire? Okay, for part A, the stress of the wire can be determined by using the formula of stress, which is stress is force per area, perpendicular force per unit area. So you just substitute the value, force is 50, cross-sectional area is 0.5, but make sure you convert this to meter. -3 times 2, which is -6. Okay, 50 and 0.5 times 10 to the power -6. Okay, and then come up with the answer. Okay, right. How about for number B, number 3B? So if the wire shows an extension of 0.4 centimeter, determine the strain of the wire. So the strength of the wire, use the equation from the strength of the wire, which is strain equal to elongation per L naught. So the elongation is given in part E, which is 0.4. But just that one is given in centimeter, convert it to meter, times 10 to the power of -2, and then divide by the L naught is 20.0 centimeter, and then you come up with the answer. Okay, then for 3 part C, calculate the Young modulus for the wire. For C, we're going to find the Young modulus. Young modulus is stress per strain. So stress is the answer from part A, and you need to divide with the answer for part B to find the Young modulus. And then the last one is the energy stored. Energy stored U equal to half FE. So half FE, E is the elongation that you can get from a part B given, yeah? And the E is given in part B, half, force is 50, and then the elongation is 0.4 times 10 to the power of negative 2. Then we come up with the answer. Okay, this one is a question number 4. Okay, based on the figure given, the two graph is given where the graph is represent the force against elongation. Okay, notice that the elongation here is given in millimeter. Both are given in millimeter, but the force applied is already in Newton. So this one, the force applied is already in Newton for both graph. It shows two wires, okay, wire P and wire Q. Okay, the first figure is for wire P. Then the second figure is for wire Q. They're having a same original length. Okay, same original length. And then also same cross-sectional area, where it is 200 millimeter square. So part A, calculate the work done to produce the extensions of 1.0 millimeter for each wire. So how to solve this? The work done can be determined by calculate the area under the graph, because the work done is represented by area under FE graph. Okay, it is equal to area under FE graph. So for wire P, okay, the work done is equal to half times, okay, find the area under graph, 1.0 times 10 to the power of negative 3, because that one is given in millimeter, and then times height of the graph for 1 millimeter. This one, the force here is 100. So that the work done here is 0.050 joule. And then for wire Q, okay, the work done also can be determined by find or by calculate the area under FE graph, where we have 1/2. Okay, for the elongation, 1.0 millimeter given in the question. So just multiply with 1.0 times 10 to the power of negative 3. So 1.0 is here, right? Because that one is a straight line graph. 1.0 supposed to be the force that we need to apply is 62.5. How to get 62.5? Okay, this 125 you need to divide by 2, because 125 is for 2 millimeter elongation, and then for 1 millimeter elongation it's supposed half of the force applied for elongation, 2.0 millimeter. So multiple with 62.5, and then the work done for wire Q for 1.0 millimeter will be 0.031 joule. And then how about P? Explain how the graph can be used to deduce the ratio for Young modulus P of a wire P to Young modulus YQ for wire Q. Right, first, okay, we need to find the ratios of Young modulus P to Young modulus Q? Of course, we need to use the equations of Young modulus. So from equations of Young modulus, we have F L naught per AE. So because that one is Young modulus P, force here, I'm using force P, right? And then elongation is elongation for wire P. But because original length and cross-sectional area for both wires is same, so I do not put the notation for the length of the wire and also the cross-sectional area. So then for Young modulus Q, we have force Q, okay, and then L naught per A, then elongation wire Q. So because original length is same, so we can cancel off this. Okay, the length can be cancelled off. The cross-sectional area is also can be cancelled off. So that if we cancel off these two, our equation will be Fp per EP. Okay, then per Young modulus Q now is FQ per EQ. Then if you notice, this Fp per EP is the gradient for wire P. Gradient what? Gradient graph. Okay, the gradients for graph F against E for wire P, and then this one is actually the gradient for graph Fe for wire Q. And then the ratios of Young modulus of wire P and wire Q can be determined by determine the ratios of gradient of the graph. So if you find the ratios, if you find the gradients of the graph, the Young modulus, the ratios of Young modulus P to Young modulus Q is 1.6. For number 5A, given here, 5A part 1, given a wire is fixed horizontally between two support 0.5 meter apart. And when the mass of 7.5 kilogram hung from a midpoint of the wire, it caused the wires to sag for a distance of 1 centimeter. And if the diameters of the wire given 2.8 millimeter, calculate the Young modulus of the wire. Okay, first, what do you have to do is to visualize the case by drawing or by sketch case. So we have this support. This one is support 1. Okay, A, terms as A here, where this one is the second support is B. So the distance between this support is 0.5 meter. So half of it is suppose 2.5 or 0.25 meter or to 25 centimeter. Okay, then the next one that we need to do is to find the distance BO. Where is the BO? BO is here. Okay, this one is B, 2.0. You need to find the length here. So the length can be found by using, and this one is theorem Pythagoras. Okay, Pythagoras theorem to find the distance BO. So then we come up with BO 25.02 centimeter. This BO is 25.02 centimeter. Okay, theta also can be determined by using just now we are using Pythagoras theorem. For the theta, we are using a simple trigonometry, so we can find the theta. So the theta now is 87.70 degree, right? And then because of this is a wire, so we have the tensions of the wire. So this one is tension 1 on the right side, which is tension 1. Here is tension 2, where this tension can be resolved to y component. So this tension can be resolved to y component. So we have this one is tension 2y, right? Another one we have tension 1y. Okay. So from that we can find the tension, okay, in the functions of mg, So this one will be the tension. Okay, we are using summation force component y equal to 0. So the force on component y here is, we have the first one is the 2y, right? So we have T2y here. And then the second one, we have T1y, is also pointing up. So it is a positive T1y. And then minus with mg equal to 0. So, so if I rearrange the formula, take mg to the other side of the equation, and we come up with 2y plus T2y equal to mg. So we come up with a formula for the tension here. The next, to find the Young modulus, of course, we need to use an equations of Young modulus. But before we find the Young modulus, a few things first we need to calculate, such as the elongation and also the cross-sectional area. We need to find these two first, elongation and cross-sectional area. So for the elongation, how we find the elongation? We are using 25.02 minus 25.0. Where is actually 25.02? 25.02 is here. Okay, the distance of OB. And then 25.0 is a distance here. Okay, this one is 25.0 centimeter. Because it occurs both sides, so I need to multiply by 2. Because it occurs on the left hand side too, so I need to multiply by the elongation for the wire will be 0.04 centimeter. And then we're going to substitute the value by using the formula of Young modulus, where this F can be substituted with tension. Okay, where is the tension? Tension is here. Okay, we can substitute with the tension. So if we substitute, then we come up with tension now is equal to mg per 2 cos theta by using this one, right? The L naught is 0.5. Substitute the values of L naught. where the L naught here is 0.5. The elongation is 0.04 times 10 to the power of negative 2 because it's given in centimeter. Okay, and then you can find the cross-sectional area by using pi r square from the diameter given. And then you substitute all the value, then simply you can find the Young modulus of the wire, which is 1.87 times 10 to the power of 11 Newton per meter square. Given number 5a part 2, the question asks to determine the ratios of Young modulus wire X to wire Y. Okay? Determine the ratios of Young modulus for wire X to wire Y. So it's given here wire X with length 100 centimeter. Okay, this one is a wire X. Given the length of wire X is 100 centimeter. The diameters of wire X is 2.0 millimeter. And then for wire Y having length of 200 centimeter. And then the diameters is 4 millimeter. Okay. So the force of same magnitude pull both wires. Force same magnitude pull both wires, and the extension X and Y produce 0.10 millimeter and 0.04 millimeter respectively. So determine the ratios of Young modulus for wire X and wire Y. Here given, here this one given Lx, right? This one is diameter dx. Okay, for the second information given, that one is for Ly. Okay, this one is for dy. Okay, then we have for elongation x. Okay, this 0.4 will be the elongation y. Okay, first is you need to write an equation for the Young modulus in order to determine the ratios of Young modulus. So let's say for wire X, this one is Young modulus for wire X. So I have Young modulus wire X is equal to F Lx. Okay, this one Lx divided by pi dx square over 4, where this pi dx square over 4 and then dx, pi dx square over 4 is the cross-sectional area, because I'm using cross-sectional area is equal to pi r square according to the formula for cross-sectional area. But I change, because the diameters is given, so the radius will be diameter per 2, diameter divided by 2, and then I need to square this 2. And then I will come up with pi d squared per 4. So this pi d squared per 4, I substitute in the Young modulus formula. Okay, so for Young modulus wire Y, so I have, this one is for Young modulus wire Y. So I have F Ly, I'm using Ly, pi dy, okay, because for wire Y, per 4, and then multiple with elongation for wire Y. So to find the ratio, we just need to divide these two equations. Okay, if I divide the equation 1 with equation 2, and then we come up with the ratios of the Young modulus X to the Young modulus Y. So I just copy back the formula, okay, from equation 1 and equation 2, and then we come up with Young modulus x per Young modulus y is equal this equation. Because the force applied is same, okay, the force applied is same, so we can cancel off the force here, right? Right. Then we have pi also can be cancelled off. 4 also can be cancelled off. Okay, so the remaining will be Lx per dx square times dx per Ly dy square times elongation for y. And if I simplify, I will come up with this formula. So when I'm come up with this formula, all the information is given in the formula. I just substitute the value in the formula to find the ratios between Young modulus x to Young modulus y. So right after I substitute the value, and then I will come up with the ratios of the Young modulus x to Young modulus y is 0.8. Okay, then for number 5b, okay, study the figure 3. From the figure 3, it shows a simplified versions of variations of load applied to a meter wire against the extensions of the wire. Then given here the initial length of the wire is 1.0 meter and the diameters of the wire is 1.5 millimeter. Okay, from the figure, calculate the stress, the work done, and also the Young modulus of the metal wire. Okay, how to do part A? Sorry, how to do number 1? Okay, by using formula stress. Stress is equal to force per area. So because for number 5B1, the question asks to find the stress when it breaks. Okay, this one is actually the breaking point. Point P is actually the breaking point. So the force that we need to refer is the force here. So the force at breaking point is 250 Newton. Sorry, the force here is 350 Newton. This one is 350 Newton. And then if we substitute the force in the formula, okay, before that the cross-sectional area is also not given, but the diameter is given. We can find the cross-sectional area by using the formula pi d squared per 4. Okay, and then we come out with 1.77 times 10 to the power of -6 meters squared. Okay, this one is for the cross-sectional area. So we substitute the values in the formula to find the stress. So stress 350 divided by the cross-sectional area 1.77 times 10 to the power of 6, and then this one will be the stress of a wires when it's broke. Okay, 1.98 times 10 to the power of 8 Pascal. And then for B part 2, the work done in breaking the wire can be determined by calculate the area under FE graph. So when you calculate the area under FE graph, you come up with the total area is 3.0 joule. So the area for FE graph is actually represent the work done. And then for B3, to find the Young modulus, of course, we need to use an equations from Young modulus formula. From Young modulus, we have this is the formula to find the Young modulus. Okay, the force that we need to refer is actually the force during proportionality limit. We cannot use during breaking point, but we need to use during proportionality limit. Please bear in mind, when we're going to find the Young modulus from a given graph, the force that we're supposed to choose is the force before the force during proportionality limit. So the force during proportionality limit is here, which is 250. So just substitute in the formula 250. Here will be the elongation or the extension, 1 millimeter. So you substitute the values in the formula. The force here is 250, and then the elongation is 1 millimeter or 1 times 10 to the power negative 3, and then simply you can find the Young modulus, which is 1.4 times 10 to the power 11 Pascal. Okay, this one is for number 5B. About number 6. Okay, for number 6, I give you the clue or the hint how to solve it. Okay, the first one is using the Young modulus equation to find force, and then equating force with the weight that we suspended on a copper wires, and then when you equating the force with the weight, simply you can find the mass from the equation.